Hi and welcome to this Applied Maths video. Today we're looking at dynamic programming, specifically Bellman's principle of optimality, but coming from a table. So in this video, we are going to look at dynamic programming as applied to some multi-stage authentic problems, such as stock control, routing problems, allocation of resources, and equipment replacement and maintenance. So the main difference between these problems and what we've seen before, these problems are generally presented to us in tables or sometimes just words. They can be a little bit trickier. And what I would suggest, if you haven't already revised dynamic programming from graphs, you should do so before going through this video. And I have linked the video that goes through dynamic programming from graphs in the description below. So example number 1 is a stock control problem. A clockmaker makes grandfather clocks during winter. The order book for clocks over the next 5 months is shown in the table below. So we have October, November, December, January, and February. And then we have some little bits of information underneath, which is the clocks are delivered to customers at the end of each month. He can make up to 4 in any month, but if he needs to make more than 2 in any one month, he will need to hire additional help at €500 per month. The overhead costs are €300 in any month in which work is done. He can put up to 2 clocks in storage at a cost of €100 per clock per month. There are no clocks in storage at the beginning of October, and there should be no clocks in storage at the end of February. Use dynamic programming to determine the production schedule that minimizes the cost. So stock control problems in general are not hugely difficult, but there's quite a lot that you need to remember. So creating a little summary for yourself can be really, really helpful. So our table is going to have our main headings, which are stage, state, action, destination, and value. So destination is a column I don't generally use when we're working with the graphs. You can put it in, but it's not completely necessary. For these questions, destination is really, really helpful. Because we're talking about practical questions, these headings will also mean something specific. So let's go through what exactly they mean. So when we talk about stage, we're going to talk about months. Now we always start with stage 1 and we work backwards. So our first month will be February. Our state, then, we need to think of what's happening at the start. So in terms of our stock, we're thinking, what do we have in stock at the start of that month? The action is then what happens during the month. So how many of these clocks do we make throughout that month? And then the destination is what happens at the end of the month. So what is left over at the end of the month? Notice with the value, I do like to put in that this question is about costs. Sometimes it's about profit. And then just to really remind myself, I have minimum highlighted, because remember, when we deal with dynamic programming questions, we could be asked to get a minimum or a maximum. To the left of my table, I have a little summary of all the information that we need from the question. The table, I've only pulled it through because I'm working on a completely different page. You'll have that from your question. No need to do that again. However, a little summary here that I have, that's really, really helpful to do, especially if the question is not laid out in a nice bullet point format. So here are some really important bits of information that we need to know as we're working through the question. So we have a max production, which means we can only make 4 clocks maximum per month. There is an overhead cost, which is 300 in any month where clocks are produced. There's extra labour costs of €500 if more than 2 clocks are made in a month. And then for storage, maximum 2 clocks can be stored at the end of the month. Storage costs are €100 per clock per month, and there's no clocks in storage at the start of October or at the end of February. So we need to bear all those things in mind as we're working through. So let's start with stage 1, which is our last month, which is February. Now, in February, we need 1 clock. So I like to put in just in this column here, and I've highlighted a different color, but how many we need for that month. So I don't have to keep going back and looking at the table when I'm filling out what's happening in that month. You don't have to do that. I just find that really helpful. So because we can't end with any stock, we need to be very careful that our destination, our end result at the end of this month will be 0. So we have two main options. So the first option is we could have nothing left over from January, which means we have to make 1, leaving us with none left over. Now, if that were the case, all that we have to think about is the fact that we have 300 in overhead costs. Because there's no other option here for this particular state, this is an optimal value. Remember, we are getting the optimal value for each of the states. If you like, you can use like a thicker line like I've done here to break up each of the states so you can see that you should have a star after each or before each of those thicker lines. So another option is that we have 1 in stock. So there was 1 left over from January. And if that were the case, then we will make none because we do not want to have any left over. We only need 1. There was 1 in stock, so we don't have to do anything. That will leave us nothing. Now, how much will that cost? So I'm going to take into account the storage costs from the end of last month to now. I'm going to take that into account in February. It wouldn't be incorrect to take into account in the previous month. You will get the same answer, even though your workings are going to look a little bit different to mine. So I'm going to put my 100 in here for the storage of that 1 clock between the end of January and February. So here I have an optimal value because there is no other options. So it's quite a straightforward first month to do. So then let's look at January. So this is stage 2 and we need 3 units. Okay, so we have a few different options here. We have a little bit more flexibility, but we need to bear in mind at the end of January, we can only be left with 0 or 1. We can't be left with any more than 1 clock. So the first option is I like to start with 0. Again, it doesn't matter which order you start in. For me, 0 is a nice logical start and I work through it that way, but it wouldn't be wrong to go from the biggest number down. So if we had none in stock, we could make the 3, leaving us with none left over. Now, how much would that cost us? So we would have overhead costs of 300 plus we have the labor because we've made more than 2 costs, so we'll have a 500. But we also need to think about, okay, if at the end of January we have 0, the optimal value then will link back. This destination of 0 will go back to the state of 0 here. So we need to include this 300 as well. Because if I have nothing at the end of January, my only option then is to make 1 in February, and that's going to cost me 300. So we're always linking back to our previous month to get our absolute total for the costs. So this is our 500 for the extra labor, 300 for overheads, plus the 300 linking back to February. That is 1,100. But the other option here is we could have actually made 4. So if we made 4, we'd have 1 left over, which is still valid. In terms of costing, we will still need the extra labor. We would still need our overhead costs. But instead of linking back that 300, we're going to have 1 left over, which would link us back to this line here, which will be an extra 100. So that's going to look like 500 plus 300 plus 100. Now, we can't make more than 4 because 4 is the maximum production. So 4 clocks per month is absolute maximum. So we can't make 5. We couldn't make less than 3 because then we wouldn't have enough units. So that's all that can happen if we have 0 in stock. So then we can say the optimal value for having 0 in stock at the start of January is 900. But we may have had more in stock. So what if we had 1 in stock? So if we had 1 in stock, again, we could make 2, which will give us nothing left over. And if that were the case, we need to think about, okay, first thing, I have 1 in stock, so I need to think about the storage. Okay, so I have to take into account my storage. We made 2, so that's 300. We don't need the labor costs in this case because that's when it's more than 2. And if there was nothing left over, we link back to this line here, which means we're adding in our 300. So we get our 300 for our overheads plus the 100 for our storage plus the 300 linking to February. Another option would be that we make 3, which will give us 1 left over. In that case, we need to think about our overheads, but now we do have to take the extra labour into account. We still have that storage because there was 1 at the start, so really think about that. Again, if you decide to put the storage in at the end, just make sure that's consistent throughout the question. There's 1 left over, which links us to this line here, which means we add in our 100. So it's 500 for our extra labour, 300 for our overheads. We have our 100 for our storage, plus our 100 if we had 1 at the start of February. It'll cost us 100 until the end. So that's 1,000. Now, I can make 4 clocks, so could I put 4 here? And the answer is no, because if I put 4 here, I'll have 2 left over, but I can't bring 2 through to February. It's not possible because February only needs 1, so I can't go to 4. Although I could produce a 4th, I can't have that extra 1 left over. So this means I've only 2 values, 700 is my optimal value, and that's all I can do if there were 1 in stock. But there could be more than 1 in stock. Okay, I could have had more coming through from December. So imagine here I had 2 from December, and then the options are I could make 1, which would leave nothing left over, and that will give me 300 for overheads. It will give me my so my 200 is coming from the 2 we have in stock, so our storage, plus 0 at the end links to this line here, which is my 300, which is our 800. Or I could have had 2 in stock and made 2, which would leave us 1 left over. So if that were the case, then we have, again, 2 from storage, that's 200. We're making 2, which is my 300 in overheads. No need for extra labour. My 1 here on my destination links me back to this line here, which is my 100. So it gives me 300 plus 200 plus 100. I could make 3, but that would leave me with too many left over to bring through to February. So these are my only 2 options. Remember, we're looking at cost, so we want the minimum. So 600 is my minimum, and that's as much as we could do. Remember, we can only keep 2 clocks in storage at the end of the month, so it's not possible to bring through 3 from the previous month. So now we move into the next month, which is stage 3, which is December. In December, we need 5 units. So because we can only produce 4 clocks maximum per month, we have to have at least 1 in stock already. So we can't start with 0 like we did in the previous months. We have to start in 1. This is what students can find a little bit tricky. So one option that you can do if you are finding you're getting this wrong is maybe to focus on doing everything but the costs, putting in all your stage, action, and destinations first, and then dealing with your costs. So then if you make a mistake, it's easier to fix, or you might be better able to spot an issue like that if your focus is not on totaling, if your focus is totally on just figuring out how many pieces you have to make, etc. So we're going to start with 1 in stock, meaning we have to make 4 in order to make our 5 unit delivery at the end of the month. It will leave none left over. For that, we need to think about this 1 in storage, so 100. We make 4, which is our overheads of 300, plus our extra labour of 500, and then there's 0. So this 0 will link back to 0 in the previous month, which is this line here. Well, actually, it's these 2 lines here, and we're taking the optimal value, which is our 900. So here we're getting our 500 over our extra labour, 300 over our overheads. We have 100 for our storage, and that 900 is coming from the destination of 0. So we had 0 left over at the end of December, which means we started January with nothing, and the optimal value if we start January with nothing was to get to our 900. So that gives us 1800. Now, there's nothing else we could do if we had 1 in stock because we can't make 5. So this is its optimal value. So we could have had 2 in stock. Now, if we had 2 in stock, we could make 3. which means we would have nothing left over in terms of how much that will cost us. We need to think about storage for 2. Making 3, which is our overhead plus our extra labor. And then again, linking that 0 back to our previous month, we're going to include that 900. So 500 for extra labor, 300 for overheads, 200 for storage, and 900 as the optimal value from January. So that gives me 1900. But we do have more options when it comes to having 2 in stock, because if we had 2 in stock, we could make 4. Remember, our max production is 4. So that will leave us 1 left over. So in that case, we need to think about storage for 2, making 4, which is our overheads, plus our extra labor. And then that 1, which is, so if we think about what's optimal there, we get our 700. So yeah, 500 for our extra labor, 300 for our overheads, 200 for our storage, plus our 700, which links to our optimal value if we had 1 in stock at the end of December or the start of January. So then we think, is there anything else we could do here? And the answer is no, because I can't make 5. So then of these 2, it's asking, well, which one is optimal? For us, which one's a minimum? And it's our 1700. So we could have 3 in stock at the start, but then we need to think in terms of our storage. And remember, there's maximum 2 in storage at the end of any month. So if you take a look at what that means for us here, we have either 0 or 1 left over. So this work that we've done here is actually not possible. Now, you might see that as you're working through the question, and if that's the case, you do not need to include it. However, you may find in these questions that sometimes you include lines that are not required, and that is absolutely fine. It is not an issue. If you sat down and spent a bit of time thinking at the start of the question, you may be able to really see what all the limitations are. So because the way that we can only make a maximum of 4 and we can only store 2, at any one time there can only be 6 within a month. So for the month of December, we could only pull 1 through. So you can stop and think about that as before you start doing your work. But if you include it, yes, it'll slow you down a little bit, but it isn't the end of the world. So then in November, so this is stage 4, we need 3 units. So then we think we have to have 1 or 2 left over. We can't have nothing. Okay, so we need to bear that in mind when we're working through November. So if we start with nothing and we need 3, we need at least 4 to make sure that we have 1 left over. Remember, we can't have 0. Now again, if you include that line, it's just a lot of extra work that we don't particularly want to do. So the costs we're going to have for this line here, we're going to make 4, which is going to be our overheads of 300, extra labor of 500. Then we need to think about, well, if we've 1 left over, that means it will cost us 1800. So 1 at the end of November means starting December with 1, 1800 total. So we get 500, which is our extra labor, 300, which is our overhead, and 1800 from the previous month. So that's our only option because we can't make more than 4 and we have to have 1 left over. So that is optimal. So if we had 1 in stock, then we have to make at least 3, gives us our 1 left over. Then we need to think about the storage for this one, which is 100, making 3, which is our 300 plus 500, and then that leftover 1, which again links to this line here, which is 1800. So we get 500 for our extra labor, 300 for our overheads, 100 for our storage, and our 1800. So that's our 2700. But we can make even more. So I could make 4 here, leaving us with 2. So our total cost in that case is 500 for our extra labor, 300 for our overheads. We have 100 for our storage of 1, and then we add on our 1700, which is our optimal value if there was 2 units at the end of November, which is the start of December. And of these 2 lines here, the optimal value is 1700. Now, I can't make any more. 4 is my maximum, so one of these two values must be optimal. So our optimal is going to be 2,600, and then we need to consider, well, what if we had 2 in stock? So if there were 2 in stock at the start of November, then we have to make at least 2 to have 1 left over. If we think about the cost there, that means we have 300 for overheads, 200 for our storage of these two, plus 1800, which is if we have 1 at the end of November, that means 1 at the start of December, which brings us back to this line here. We could equally make 3. And if we make 3, that will leave us 2 left over. And in terms of cost, that's going to be 500 because now we have our extra labor, 300 for our overheads, 200 for our storage. And then because this is 2, we have our 1700 here. So that is our 2700. Now, could we do any more? Yes, we could make 4. But that would leave 3. And remember, we can only store a maximum of 2. So there isn't actually anything we can do to carry over. So the optimal value of these two is going to be our 2,300, and that ends our November. So then we need to think about our last month, which is stage 5, which is October. In October, we want 2 units. So in terms of our options, remember that they told us that there are no clocks in storage at the start of October. So the only thing we can have here is having 0. If we have 0, we have to make at least 2 because we need 2 for that month. If we make 2, that gives us 300 for our overheads. And then we think about if I end October with none, it means I start November with none, which gives me my 2,600. I could make 3, which would leave 1. In that case, we have our extra labor costs plus our overheads. And then if we've 1 here at the end of October, that's 1 at the start of November, and that max or the minimum here, our optimal value is 2,600. And then our third option here is we make 4, which will leave us 2 left over, which is 500 for our extra labor, 300 for our overheads. And if there's 2 left over, the optimal value of having 2 at the end of October, or rather 2 at the start of November, is going to be that 2,300. So it gives us 3,100. Now, of those 3, our optimal value, so we're thinking cost, it's a minimum, so it's 2,900. So in terms of our final question, what is the minimum cost? And the minimum cost is 2,900, which we can read directly from here. Now, in terms of what is the optimal production strategy, so the first thing we can see is, okay, we want to make 2 in October, and then that will leave us nothing in November. So we have to go to this line here, and then that means we make 4 in November. There's 1 left over, so this 1 at the end of November brings us to 1 in December. So we have 1 in December, so our optimal strategy there is to make 4, and there's nothing left over at the end of December, so nothing in January. So if there's nothing in January, this is our optimal strategy for at the start of January. If there's nothing left over, then our optimal strategy is to make 4. There'll be 1 left over, which gives us this optimal strategy here, which is a 1 at the start of February, and we make none. So we are not just looking at our final number answer, but we're also thinking in terms of our strategy. When we're dealing with the graph, we would think about this as our path. So you don't have to think about it as a pathway because it's not a graph. We are thinking about it as a strategy. So example 2 is a routing problem. So Toby has a fairground ride and will take it to 3 county fairs over the next 3 weeks. He will leave home at the start of week 1 and travel to the first fun fair, then go to the second fair for the second week, and then go to the third fair for the final week before returning home. There are 7 fairs during the next 3 weeks, so there is a choice of fair each week. Toby must decide which one of the fairs to go to. So we're provided 3 tables. Table 1 tells us which fairs are on which week. So we can see week 1, it's fairs A and B. Week 2, fairs C, D, and E. And in week 3, there's fairs F and G. In table 2, it gives us the profit per fair, which is in hundreds of euro. And then in table 3, there is the travel costs in hundreds between each of the fairs and home and each other. So Toby wishes to maximize his income, use dynamic programming to determine the fares he should go to and his total income. So let's keep these tables beside us so we can fill in the table as we go. Anytime we're working with dynamic programming, we always start with the same: stage, state, action, destination in these questions, and then value. And then we need to think about what do each of these mean in the context of the question. So stage is like the weeks remaining. So that can be tricky to understand. But remember, if we are at the start of the first week and we don't get home till the end of the third week, we end up with like 4 weeks. So when we talk about these states, it's how many weeks remain until he gets home. You don't have to worry too much about that, but sometimes that causes confusions for students. So the state then is the start location. The action is then any travel or the journey that he's going to do. The destination is then the end location, and the value in this case is a profit. So we're thinking in terms of a maximum. I like these questions because these are quite close to our graph questions. They use nodes, they're quite straightforward to work with. I think this is like the closest to a graph question we can get without having a graph. So let's start with our week 3. Remember, we always start at the end, which means we're in stage 1, but there are basically 1 week. There is 1 week to go before the end. Then you might say, well, we're in week 3, but he is at the start of week 3 and he doesn't get home till the end of week 3, or you can think of it as the start of week 4. So he can either start at F and then he'll have to travel F to home, which leaves him home, or he can start at G and then go G to home, which means he ends up at home. Now, what I like to do for these kind of questions, and you can apply this logic to any question, is actually fill out the whole table first and then come back and do my calculation. Now, some students prefer to do the calculation as you go, like we did in example 1, but it's absolutely fine if you want to kind of complete your table first. It takes a little bit less thinking, and then you can really focus in on your values. So you're not trying to do 2 things at once. So I'm going to do this particular question by filling out the stage, state, action, and destination completely, and then going back and filling in our value. So remember, we're always trying to get the optimal value per state. So I'm going to draw my little line in between F and G, and then that's the only option for stage 1. So for stage 2, then we have 3 options, C, D, and E. So if Toby goes to C, he has 2 options. He can go C to F, which means he ends up at F, or C to G, which means he ends up at G. If he is at D, he then has D to F or D to G. And then if he goes to fair E, he can go E to F or E to G. So that's our stage 2. So when there's 2 weeks remaining from the end. We then think about our last and final stage, which is stage 3, which means there's 3 weeks to go. We're really talking about the start of week 1. So our options are, there is a fair A. So if Toby is at A, he has 3 options. For week 2, he can go from A to C, he can go from A to D, he can go from A to E. There is then also fair B. And if he's at B, he can go B to C, B to D, or B to E. Now, you might think he's done, but remember, he had to start and end at home, which means at the last stage, so stage 4, and again, you might be like, there's only 3 weeks. But if we think about each of our stages, so we're at the very start of our week 1. So here, he has to start from home. So here at home, he can either go to Fair A or Fair B. So that's our table complete. And that didn't take a huge amount of time. Our thinking was quite limited. We didn't have to do anything hugely complicated. Like I said, I like these questions because we're working with nodes. We tend to work with letters. It's easy to kind of see how this ties into our dynamic programming from graphs. Now what we can do is we can really focus on the value column and getting that worked through and just focusing on our numbers. So let's start with our first piece. So there are, again, 2 different ways where you can approach this. So one option here is to look at F and say, okay, we started at F, so we have our profit at F, and then the cost to travel home. So bear in mind that table 2 is profit, so plus, and table 3 is costs, which is minus. So you can put your profit of F and then take away the cost to travel home. Or you can ignore the profit at F and only look at the profit for the destination. So you can decide whether to take the profit at the state, so at the start, or at the end. I'm going to do it at the start. So for us here, what I'm going to say is for that first line, I have F, so the profit will be 14, and then to travel from home to F, which is the same as F to home, is going to cost 800. So we end up with 14 minus 8, which is 6. Because we always take the optimal value at each state, this is optimal. Then we have G. So the profit at G is 12. Home to G is 7. So we have 12 minus 7, which is 5. Again, we always take it optimal at each state. This is the only thing we have for this particular state. So this is also optimal. We then have C to F. So we're going to start at C. So our profit at C is 8. To travel from C to F is 5. And then we need to consider, but if I'm at F, the optimal way to get back is going to be 6. So that gives us our 8, which is our profit for C, minus 5, which is the cost to travel from C to Fair F, plus our 6, which comes from this line above. Then if we go C to G, we again have that profit 8 at C. We then go C to G, which is also 5. But this second 5 comes from the fact if we end up at G, to get from G back home is going to take 5. Now, of those two, we want, again, focus on this idea of maximum. It's so easy to mix up minimum and maximum in these questions. We are dealing with profit. That's why I've subtracted costs. So our maximum or our optimal here is going to be 9. For D, then, we have a profit of 10. Traveling D to F is 4. And then if we're at F, we need to take into account that it is 6. So we have 10 minus 4 plus 6, which gives us 12. Again, D to G, same profit. D to G is only costing 2. So this will be 10 minus 2 plus 5, because if we end up at G, G to home has an optimal value of 5. Again, we want the maximum. So here is our maximum. It's 13. We then look at E. So our profit at E is 11. We then have to travel E to F, which is 4. So that gives us our 11 minus 4. If we end at F, that gives us an optimal value of 6, which we're adding on. E to G, same profit. E to G is a cost of 1. And then we'll bring in the cost from G, which is 5, or the profit, sorry, from G, which is 5. So 11 minus 1 plus 5, which gives us 15. And then the 15 is optimal. So then we look at the next stage. So then we're working with A. So the profit at A is 6. And then the cost to travel from A to C is 3. And then if we ended up at C, the optimal value for C is the one we've starred, which is 9. A to D has the same profit, but traveling from A to D is only 2. And if we end at D, its optimal value is 13. And then our last one within that state is A to E. So same profit, A to E is 1. And traveling A to E is 1. Right, A to E is 5. So you have 6 minus 5 plus 15, which gives us 16. We then look at which one here is optimal, and our 17 here is optimal. Then we move on to B. So the profit at B is 5. Traveling B to C then is 1. And then we're adding on what happened at C. So our optimal value at C is our 9. We then are B to D, so same profit. And then if we travel from B to D, we get our 3. And then if we're at D, the optimal value is 13. And then last within that state, we have B to E. B traveling to E is 3. So that gives us 5 minus 3. And if we're at E, the optimal value is 15. Of these three, our optimal value is 17. And then we just need to think about the last step, which is in the terms of the question, the first bit of travel, which is getting from home to the first fair. So they're starting at home. So if Toby is starting at home, his only two options are either to go A and B, because that's all we have at the fair. Because we always took so far the profit for the fair at the state, so at the start, we don't have any profit. All we have here is our cost plus the optimal value. So the cost to go from home to A is 3, and then we add on what it would be the optimal value if we were at A, which is 17, which gives us 14, and then home to B, which is 2. So minus 2 plus 17, which gives us 15. So our optimal value is 15. So this means our maximum profit is 15. And in terms of fares, Toby should attend B first. So in week 1, should go to B. And then if he goes from B, the optimal value then tells us to go to E in week 2. And if he's in Fair E at week 2, optimal value says go to G for week 3. And he starts and ends that at home. So example 3 is allocation of resources. A fruit grower can use his surplus crop to make into jam, tinned pie filling, or dried fruit. He can process up to 5 units of fruit, and the expected profits in hundreds of euro from making various products are shown in the table below. He will use all 5 units to make these products and wishes to maximize his income. So here is our table, and for each of the units of fruit, it is his income in hundreds. Using dynamic programming, determine the number of units he should allocate to each product to maximize income. So there is no real flow in these questions, not like in our previous ones where there's like months or weeks. So technically the order here that you do it wouldn't matter. I do suggest using your table so you don't get confused and starting at the bottom and working back. But really it won't change the question if the order of these products is changed, because they don't have a flow or a timeline to them the way our other questions had. So the first thing we're going to do is we're going to set up our normal headings, which are stage, state, action, destination, and value. So this is quite a long question. And I find for these allocation questions in particular that it is easier to fill in the stage, state, action, destination first and come back and do value. So let's now identify what each of these headings mean when we deal with an allocations question. So our stage is which product we're dealing with. Like I've already said, the order isn't important, but I'm going to work from the table going from the bottom to the top just to keep it clear. The state, think about the state as the start. So how many units are there available to be allocated? The action is then what happens within that. So how many units are we actually allocating? And then the destination is the end. So how many are available at the end? So what is remaining? In terms of our value, we're talking about profit this time, so we're thinking as a maximum. I don't have a huge amount of space, but I'm gonna put my table in here. I don't think it will block anything, so we can see what's going to happen. So let's start with stage 1, which for us product-wise, we're starting at the bottom. This is dried fruit. So there's absolutely no limitations on what could be used. It is possible that they say, oh, you must use 2 units of jam, or you must have at least 1 unit of each. In this question, it's completely open. We can have 5 units of the same thing without issue. So it is possible by the time we get to the end that we actually have nothing left to allocate to dried fruit. And that means we can't allocate anything and there's nothing remaining. Another option will be that we have 1 left. But here's the thing, if I have 1 available at the end, I have to allocate it. So basically within stage 1, our destination has to be 0 for every single one of these. So that makes it a little bit quicker to kind of work through. So I could, in theory, have up to all 5 units left. These darker lines, remember, show us each of the states, and within each of the states, we need to pick an optimal value when we get to the value part. So this is our breakdown of our first product. The second product is always the longest because there's a lot more, there's much more variation in what we could do. So our stage 2, our second product, is the pie filling. So for the pie filling, again, by the time we get here, there may be nothing left. Now, if there's nothing left, there's nothing to allocate, so we can't leave anything through. If there is 1 unit left, then we start having a few options. So I could allocate all 1 of those units to pie filling and have nothing left, or I could keep that, so give nothing to pie filling and leave 1 left over, which can go to dried fruit. That's my only 2 options within that state. So if there was 2 left, you can maybe start seeing a pattern. And this is why I like to do all this work first, so I can really get into the pattern and make sure I have this complete before I start talking about my value. So for 2, I could allocate all 2 and leave nothing. I could allocate 1 and leave 1, or I could allocate nothing and leave 2 for the dried fruit. For 3, I could allocate all 3. I could allocate 2. I could allocate 1, or I could allocate nothing. And then this will be on 1 page for you. I have to split my screen because of the orientation of it. So I am looking at state if there is 4 available. So 4 units available. That will give us either 4 to allocate for pie filling, or 3, or 2, or 1, or nothing. So there's 1 last state that could happen with the pie filling, and that is if all 5 is left over. So if all 5 is there, we can allocate all 5. We can allocate 4. We could allocate 3, 2, 1, or nothing. Nothing is absolutely valid here. So you can see there the pie filling piece is quite long, which brings us to stage 3, which is for us jam. And the options are, well, because jam came first, there's only 1 option. There's 5. So it's how are we allocating these 5? So 5 could be allocated, leaving us with nothing, or just 4, which would leave 1, 3, 2, 1, or nothing. So now I have my table ready to go, and I feel like that it can be very quick, especially for these longer questions. And now our focus is just on finding the profit of each line. You have to pay a lot of attention. Remember that the destination in 1 stage links back to the state in the other. I'll do my best to kind of highlight and point them out as we go. So our first section is lovely and straightforward. There is no profit if we don't allocate anything to dried fruit. If we allocate 1 unit to dried fruit, we get our 8 that's here. Now, within each of these darker lines, remember, these are all our individual states, so we need an optimal value within here. So 0 is technically an optimal value. Our next one is 8. That's also optimal. We then have 16, which is optimal. And then we have 24, 32, and 40. So this is nice and straightforward to fill in for our first stage. And we haven't confused ourselves by having to think about that while we were also trying to figure out how many units we had and we're taking them away and so on. So when we get into stage 2, this is always the trickier one because there's so much going on in stage 2 when we're doing allocation of resources. So the first option is 0, 0, 0. So if you don't allocate anything to pie fillings, there's going to be nothing. But we also need to think about the destination here, which is 0, which links to this line here. So effectively I get a 0 plus a 0, which is a 0. This is optimal because that is the only thing that's happening at that state. Then if we allocate 1 unit for pie filling, that is 16. So we have our 16 there, and then we also have 0 left over. So that's going to give us 0 from the previous step. So that 16 plus 0 gives us 16. If we allocate none of that, we'll have 1 left over, so we'll get a 0 plus that 1 is going to link back to this line here. So we get 0 plus 8, which gives us 8. Remember, we're doing profit, so we're trying to maximize it. So this is 16. Then we think about if we have 2 units of pie filling. So we have our 18 there. Okay, so we could have 18 if it's 2 units, 16 if it's 1 unit, and 0 if it's no units. So we have, in the first case, nothing left over, which again is linking to that very top line up here. So that's our 0. And that's giving us 18 plus 0 equals 18. If there's 1 left, that's our line here, which is 8. So we have 1 unit that's allocated, which is 16, plus our 8, which is pulling from our optimal value, which gives us 24. And then we have nothing for pie filling, which is 0, plus we'll have 2 remaining. And if we go up here to where there's 2 remaining, we add our 16, and that gives us 16. So our optimal value here is our 24 in the middle. So then if we have 3 left over, we could allocate all 3. All 3 will give us a 20. That's how much we get profit-wise. And we have to take into account the 0 from our previous stage. So that's 20 plus 0. Otherwise, we have 18 plus 1 from our previous stage, which is 18 plus 8, which is 26. Or we have 1 allocated with 2 moving forward into dried fruit. That gives us our 16 plus 16, which gives us 32. Or we've no allocation to pie filling, which gives us 0 plus, if we link that 3 back to our stage above, it's 24. So 0 plus 24 gives us 24. The optimal value there is our 32. Then we think about if there was 4 units to allocate. So if we had if we allocate all 4 units, that's going to be 22. So we get 0 left over, which is adding our 0. 22 plus 0 is 22. If it were 3, we get 20 plus 1 left over is 8. So that gives us 28. If we have 2 allocated with 2 left over, that's 18 plus the 16 from before, which gives us 34. If we allocate 1, that's 16, plus the 3 that's left over brings us back to 24. So 16 plus 24 gives us 40. And then lastly, if we allocate none of that, that'll give us no profit there. Plus, if we leave 4 left over, that will give us 32. So our optimal here is 40. So this is our last state within the second stage. If we had an allocation of 5 ready to go, we could allocate all 5, which will give us our 24. So if we get our 24 plus the 0, which is 0, which is 24. We could also just allocate 4, which would be 22, plus that 1, which is 8. So 22 plus 8 is 30. Or we could allocate 3, which is 20, plus 16, which we're getting from dried fruit if there was 2 at the start. If we allocate 2, that's 18, plus what we get as the optimal value if there's 3 remaining is 24. That's a total of 42. We could then have just 1 allocated, which is 16, plus our 32, which gives us 48. Or we could allocate none of that, which is 0, plus our 5 here links back up to the left to 40. So that 0 plus 40 gives us 40. And our optimal value here is 48. So now we're moving into our last stage. So our last stage is at the very start. There was 5 to begin with. So either we allocate all 5 for jam, which is up here, and that is 38. And then we need to think about that 0. So that 0 goes back to stage 2. So it's this line here. So it's I have 5 allocated, which is 38 plus 0, which just gives me 38. For 4 allocation, I have 36 plus this 1, which links to this line here, which is 16. So 36 plus 16 is 52. If I then allocate 3, we have 33 plus this links back here to 24. 33 plus 24 is 57. Or if we allocate 2, 2 is 27. 27 plus our optimal value for 3, which is this line here, which is 32. That gives us 59. Or if we allocate 1, which is 12, that leaves us 4. 4 then is up here. If we have 4 left over, the optimal value for it is 40. And then finally, if we don't allocate anything to jam, we have our 5, which is this line here, which is 0 plus 48. Our optimal value here then is 59. So then we need to think about, well, what is the best strategy? So we can see the maximum profit here is 59. Remember, we're working in hundreds. That's 5,900 or 5,900. In terms of the most profitable strategy, we have this line here. I'll actually do it in highlighter. So we have this line here, which means we allocate 2 to jam, and that leaves 3 left over. So we come back over here to 3 left over. So for pie fillings, we'll have 3 left over, and the best strategy is to allocate 1 unit. And then when we come back up here, there'll be 2 left over. So it's this strategy here. So that will be 2 left over. So 2 allocated to dried fruit. Example 4 is an equipment replacement and maintenance question. So an Uber driver purchases a new electric car for work. The car costs $28,000 to buy, and its maintenance costs increase with age, as shown in Table 1. The resale value of the car also decreases each year, as shown in Table 2. For safety and insurance reasons, the car must be replaced after a maximum 4 years of use. The driver plans to work for the next 6 years and wants to determine when to replace the car in order to minimize the total cost over that period. She will always own a car, i.e. a replacement is bought in the same year as the previous one is sold. So here are 2 tables. Table 1 is the annual maintenance costs. If the age of the car is under 1, it costs nothing. If it's 1 year old, it's 400. 2 years, it's 650. 3 years, it's 1,000. So the resale value is a car that's 1 is 21,000. If it's 2, 16,400. If it's 3, 12,000. And if it's 4, it is 8,000. Use dynamic programming to determine the minimum total cost over the 6 years. You must decide when the Uber driver should replace her car, clearly identify the optimal replacement schedule, and state the minimum cost over a 6-year period. So this is one of the types of questions students struggle with the most, and often it's because of how they think about this question. What I suggest to do is to simplify this question hugely by thinking in terms of always getting the cost over the lifetime of the car when you buy the car, rather than trying to break it down year by year, because that's going to be way too complicated. So for example, this car costs 28,000 to buy, and here's our our costs and our resale value. So if I buy a car or keep it for 1 year, the cost is 28,000 to buy it minus 21,000 for the resale. So actually it costs 7,000 to own a car for a year. If I buy a car and keep it for 2 years, it costs me 28,000 to buy, but then in the second year, when it's a year old, I have to pay my 400 for maintenance minus the resale cost, which is 16,400. So it costs me 12,000 overall if I own a car for 2 years. For 3 years, it is 28,000 plus 400 for the costs in the second year and 650 for the costs in the third year, minus 12,000, which is the age of the car, which is the resale value of a 3-year-old car, and that gives us 17,050. And if you buy a car and keep it for 4 years, the total cost is 28,000. Then you have your maintenance, which is 400 plus 650 plus 1,000 minus the resale value, which is minus 8,000. So every time we buy a car, we need to think in terms of how much will that car cost overall. So you can do this little bit of work before you start. I'm going to have it broken down in my table anyway, but if you want to simplify your question, you can literally be filling these in as you go. So here are my little calculations on the left to help me, and here is our table. So we have stage, state, action, destination. I have the value as a calculation and then the total cost, but that can all just be one column if you prefer. What I want you to really think about in terms of this question is stage is each of the years. That's straightforward. For state, it's like what is the start. So it's going to be the start of a year or possibly the end of a year. The action then, I find this easiest if you think about it in words. And I'm actually going to write it in words. It's what do you do? So it's going to be I buy a car and keep it for this long. We don't care about cars that you've previously purchased. We only care about new cars. Because if you've previously purchased them and we've taken into account the total cost over its lifetime, we don't have to worry if you have a car that's a year old. It completely simplifies the question. It makes this so much easier to understand. The destination is then how long until I sell that car. So the state or the start of is really like when do we buy the car, and the destination is when do we sell it. We only care about buying and selling. I don't care about a car that I'm in the process of owning, if you can make sense of that. And then our value cost calculation. So because it's cost, we're going to try and minimize that, and you'll be able to see that total cost. Because of the work we've already done over here, you can do this so much quicker. I'm going to really break it down because it's an example, but don't feel you have to. So I'm going to start with stage 0, okay? And I find that's really helpful in these cases. So we're working over 6 years. So I'm talking about the end of year 6. So there's no action. We get to the end of year 6 and nothing happens. So why am I putting it there? Well, remember, we have to link our destination to the state. So if you left this out, it wouldn't be the end of the world, but I do think it helps us make more sense of what's going on. So stage 1, we're talking about the start of year 1. The action is then, the only thing I can do at the start of year 1 is buy a car and keep it for 1 year, which will bring me up to the end of year 6. That's the only thing I can do. So I start of year 6, I buy a car and keep it for 1 year. Now you might say, but what about if we'd had a car already? We'll have dealt with that somewhere else in the table. We only care about buying the car and how long we keep it for. So that means we have a total cost of 7,000. So it's 28,000 minus our 21,000, which gives us our 7,000 total. So then if we think about is there anything else we could do? And it's like, no. So that value is optimal. That 7,000 is the optimal value. It's the only thing we can do if we end up at the start of year 6. But here's the thing, we may not get there. We may hold on to a car in such a way that we don't have to do anything at the start of year 6. So stage 2 then is the start of year 5. So at the start of year 5, we have 2 options. Option 1 is we buy a car and keep it for 1 year, which will bring us up to the start of year 6. So now we need to think about, okay, well, the start of year 6, then if we get to there, we need to also buy this car. So at the start of year 6, if I buy and keep it for 1 year, that is our 7,000. Plus, I need to take into consideration that 7,000 as well. So I have my 28,000 minus my 21,000, which is 7,000, plus my 7,000, which is 14,000. So then this kind of explains, well, what happens if we don't want to buy a car in year 6? Well, what happens at the start of year 5 if we buy a car and keep it for 2 years? So that will bring us up to the end of year 6. And the end of year 6, there's nothing. We don't have to add on anything for that. So for 2 years, we are going to have this calculation here. So our 28,000 plus our 400 minus our 6,400, which gives us our 12,000. So then that's all that can happen. If it's the start of year 5, we only have 2 years, so we can either buy it for a year or buy it for 2 years. They're our only options. So the optimal value here, remember it's cost, we're doing a minimum, that's our 12,000. So then we have stage 3. Within stage 3, we have when we're in stage 3, our state is the start of year 4. So we have a few more options here. So we can buy it and keep it for 1 year. That will bring us up to the start of year 5. So again, start of year 5, we're now brought here. Remember, our optimal is 12. So if I keep it for a year, I have my 7,000 plus my 12. You can see how much simpler this is if you've done all this work before you start into the table. Again, I'm showing my full breakdown. You don't need to. You can go straight to 7,000 plus 12,000, gives us our 19,000. Equally, you could buy something and keep it for 2 years. That would bring us to the start of year 6. Start of year 6, our optimal value is 7,000. So if you have 2 years, that's 12,000 plus our 7,000. And that gives us a 19,000 as well. Or you can buy it and keep it for 3 years, which will bring it to the end of year 6. And remember, at the end of year 6, there's no cost to it. So if we keep it for 3 years, that gives us our 17,050. So you don't need to keep showing all these calculations. You can just take our numbers straight from here because they're going to be the same calculation. But simplify the question to focusing on putting in the value, the total cost when you buy that equipment. So then in stage 4, our optimal value then is our 17,050 because again, cost, we're looking at minimum. For stage 4, our state then, we're at the start of year 3. So we have 4 options there. So again, if you wanted to work this through by filling in the action and destination before the calculation, that's fine. I actually find this one, I tend to do the calculation at the same time, but it doesn't matter. Once the end result looks the same, it doesn't matter what order you do it in. So we can buy and keep it for a year. That will bring us to the start of year 4. So if we're talking about the start of year 4, it links to here. So we have a 17,050 to bring in. So we have our 7,000 plus 17,050, which gives us our 24,050. If we buy it and keep it for 2 years, it brings us to the start of year 5. So our optimal value with that is 12,000. So that's 12,000 plus 12,000, which gives us our 24,000. We could buy it and keep it for 3 years. That would bring us to the start of year 6, and our optimal value is 7,000. So we have our 17,050 plus our 7,000, which gives us our 24,050. And then we could buy it and keep it for 4 years. That would bring us to the end of year 6. There's nothing involved in that, so it's just going to give us the 22,050. And our optimal value there is 22,050. Stage 5 will bring us to the start of year 2. Again, we can only keep a car for 4 years max. So we need to kind of bear that in mind because you can't buy it at the start of year 2 and keep that same car. So we could buy a car and keep it for 1 year, which brings us to the start of year 3. That gives us our 7,000 for buying it and keeping it a year. If we go back to the start of year 3, our optimal value is 22,050, so we get 7,000 plus our 22,050, which gives us 29,050. We can buy it and keep it for 2 years. That brings us to the start of year 4. That gives us our 12,000, and then the start of year 4, the optimal value is 17,050. That gives us 29,050 as well. We could buy it and keep it for 3 years. That would bring us to the start of year 5. So for start of year 5, it means we are linking to 12,000. That's our optimal value. If we keep it for 3 years, 17,050. So 17,050 plus our 12,000, 29,050. And our last option is to buy it and keep it for 4 years, which gets us to the start of year 6. And that's a 7,000 optimal value. So 22,050 plus 7,000, which gives us 29,050. All of these are the same number. So these are technically all optimal. So what happens in a case like that? Well, if this were to come up in an exam and you see something like this, we would hope that actually this is not part of the optimal path. And it's not. It's not going to be part of our optimal strategy. So actually it doesn't really matter. So don't panic if this happens. And if it happens and it's part of your answer, it's a little bit trickier. It means something probably has gone wrong, unless they use maybe 2 values and they've specified that there's 2 options. So our last stage then is stage 6, and that's the start of year 1. So we could buy something and keep it for 1 year. That brings us to the start of year 2. That gives us our 7,000 plus 29,050. It doesn't matter which value we use because they're all the same. So it doesn't matter, we have 4. And that gives us 36,050. We could buy it and keep it for 2 years, which brings us to the start of year 3, which gets us 22,050. Plus our 12,000, and that's 34,050. Could buy it and keep it for 3 years. That brings us to the start of year 4. So the start of year 4, our optimal value is 17,050. So 3 years, our 17,050 plus our 17,050, that's 34,100. And our final option is we buy and keep it for 4 years. That would get us to the start of year 5. Optimal value is 12,000. So that's 22,050 plus our 12,000. And we get 33,950. So that is our optimal value there. So our minimum total cost is 33,950, and the optimal replacement schedule is to buy at the start of year 1 and then keep it for 4 years. That brings us to the start of year 5. At the start of year 5, the optimal value is the optimal schedule then is to buy and keep for 2 years. So this really simplifies those types of questions. It is a very different way to approach it than maybe you might instinctively think. So a bit of practice on these, and hopefully you will find the questions linked in the description below helpful. Up to the 2024 exam, this hasn't actually been examined. We haven't seen dynamic programming in this form. I have attached in the description below a set of questions from a different exam that will mimic the kind of thing we would expect to see in the Leaving Cert.